All right. So we just finished and we got C1 equal to C2. C1 equal to 0 and C2 equal to minus delta. So there's still two things that we don't know. We don't know what the value of delta is, and we don't know what the value of k is. But we do know that k is equal to p over square root of e to the I z. So the only thing we really don't know is p, right? So to help solve for the two unknowns, we're going to apply the last boundary condition, which says that VC of L is equal to delta 1 minus cosine of k L. All right. So for this to be true, we know that at VC of L, we know that the displacement is equal to delta at that point. So the only time that can be true is if cosine of KL is equal to 0, which we also know is when cosine of square root of pi e to the I z times L is equal to 0. And that's only will happen when KL is equal to n pi over 2, where n is an odd integer like 1, 3, or 5. Right? So we can now set P, this square root of p over e to the I z L has to be equal to n pi over 2. So this is just k here, right? And then if we rearrange and solve for p, what we end up getting is p is equal to n squared over pi squared divided by 4l squared times e to the I z. So p is going to be the lowest when n is equal to 1, right? So, all right. So the critical load, or the load, so if P is less than P crit, no buckling will occur. If P is greater than P crit, greater than or equal to P critical, buckling will occur. All right. So this equation here is only true for fixed free boundary conditions. Right. So we will talk about the other boundary conditions, such as fixed free, pinned, etc. on the next slide. So I just keep going here. All right. So so if we just plug in our value of k, um, so 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 we know that the displacement of v sub c of x is equal to delta times 1 minus cosine of pi x over 2l. Delta is still unknown. You can't predict it using Euler theory. All right, so delta will still remain unknown, but we can predict whether or not something will buckle. All right, so in general, so if we only considering different n cases, p critical will be equal to this term, all right, here, and the constant k in this case will be a function of the n condition. So if it's pin, or fixed free, that will modify k, all right? And then for the critical stress, we can write that as being equal to the critical force over the area, all right? So if we plug in the critical force here, all right, we can rearrange this in terms of some, I guess, more useful values in terms of normalizing different types of columns. So one of the terms that that people have developed to normalize everything is called, one of them is called the radius of gyration. So this is referred to as RG, which is just equal to this square root of the moment of inertia over A. All right, and if we take that RG term and we put it in to the original equation, we can put it in the denominator of the equation, and then if we look at that and we separate the length divided by the radius of gyration, we can develop this other parameter, which a lot of times we'll call the slenderness ratio. So basically, how long is the column relative to the cross-sectional area and moment of inertia, essentially, is what that slenderness ratio is. So you can think of this as normalized column length. Right. So for very small L over RG, the column may fail due to yielding instead of buckling. So in theory, Euler's curve would look something like this, but in reality, you'll meet the yield stress or the critical stress before Euler's curve would predict it. So, in short, short columns will fail due to plasticity before they buckle. And then the last thing in this video we have is that we have another example. So an example, read on your own. All right, and this deals with an intermediately supported column. All right, so just read this on your own, and that concludes video 1.